Okay, good morning, everybody. I hope everybody is doing well. Um, okay, anyway, let's go to the browser here. Sorry, looking over some notes and some information. So we're gonna go over to the browser, and we're gonna take a look at some things that I uploaded or something I uploaded for you guys yesterday and last night or yesterday afternoon. So we look at 262, going to our online transition. And of course, we have our lecture videos here and then the examples here for series. Now, I highly recommend um, what you guys do is definitely look over some of these examples. I highly recommend that. Let's see if I can make this bigger. Just kind of curious. No, I guess not. Ah, I don't know. Whatever. Okay. I highly recommend what you guys do is look over these examples because I did a lot of examples for you guys of geometric series. I did some telescoping series and I did some tests for divergence. Now, this is some extremely important information that you guys need to know how to do. So I went through some details here for you, and it was uploaded for you guys. And so make sure you put some time in to double check and look over those kind of examples. It's examples that we worked on yesterday. So take a look at that, okay? Because today what we're going to do is we're going to work with another kind of test for series, and this is called the integral test. So the integral test for series, let's go back to find it. Here we go. Okay, here's the integral test for series. Let me write down what this test actually is. And the integral test, of course, involves an integral. So let's remember here a few things here. All right, I'll write down integral test. Right? It's an integral test for a series. And let's remember we can describe every series here, right? AN is actually Fn, where n is a natural number. In other words, my domain here for the function, the domain is a set of all natural numbers. And that's where we really start. And so here's what the integral test is going to be. There we go. Let's make that straight. Okay. We're going to let f be a continuous function. That's one thing. It has to also be a decreasing function. And we also say it needs to be positive and a positive function. And that's going to be over the interval from 1 to infinity. Okay, and so being strictly positive means f of x is greater than 0. So you have to have a continuous function. It's going to be a decreasing function, and it's going to be strictly a positive function over that particular interval. So we're going to set this theorem up. And, I think let's double check what your book has. Yeah, we're good. Okay, we're good. So here's what they want to say. Then the series AN, for n is 1 to infinity here, is convergent if and only if, that means equivalence, the improper integral from 1 to infinity of f of x dx is convergent. So let me write this down and emphasize the meaning of these phrases, because that's an important detail for people, right? This is what this means. This is an equivalence relation, ladies and gentlemen. It's a biconditional. That means it goes both directions. Biconditional. Because typically you have something like P, you have a conditional. Well, this goes in both directions, meaning if you have P, then you have Q. So if P, then Q. You also have if Q, then P. You have what's called the inverse. So it goes in both directions, and that's important. You also have the contrapositive. In other words, this statement is very deep. This also implies the following, that your series AN is divergent if and only if the improper integral from 1 to infinity fx dx is divergent. So this is an extremely important test, and it really applies to particular cases. You might say, what cases does it apply to? Well, really, they're going to give you continuous functions. They're going to give you, terms are going to be strictly positive, but it applies strictly to decreasing functions. And so this is kind of a test that, it's a very good test. And what I'm going to do here for you guys this morning is I'm going to prove the infamous harmonic series that I said to you guys. If you guys recall, we have a special series called the harmonic series, and it diverges. So our harmonic series diverges, and you say, well, what's the harmonic series? Well, it's 1 over n goes to 1 to infinity. So the terms here look like 1 plus 1/2 plus 1/3, and so on. And so this comes from the idea of the function you have being 1 over x, and I'll do this here. 1 over x, the graph looks like this. You guys remember? And it has, it's a hyperbola. However, in the function f of x being 1 over x, notice the important fact here is that it's decreasing. It's strictly positive, meaning it's above the x-axis, right? Decreasing, and it's continuous everywhere except 0. But it's continuous over the interval from 1 to infinity. So it has all the nice criteria that we're talking about. But this is a function. And you say, well, what does the series look like? Well, it's not to scale. If we did draw it to scale, it would look closer to something like this, right? Here's going to be that first point. N is 1, this is when n is 2, it's 1/2. Now it's 3, and so on. And if we had a curve, definitely would get close to the x-axis and actually close to the y-axis here as well. But yeah, trying to draw upside down really. So to show you here this function, yeah, it's actually strictly decreasing. It's positive above the x-axis, and it is continuous over that interval. We could use the integral test. So when you use the integral test, though, right, what we're going to do now is integrate from 1 to infinity 1 over x dx. And so this is an improper integral. So we're writing this down here. Okay, so you're going to replace here, you're going to use the fact that an can be described as a function, fn, where the domain here is natural numbers. However, when you integrate over by the improper integral, you have to have a real variable, right? This is x. Domain has to be an interval, not discrete points. So you're going to use this to test. We're going to use this improper integral here. And if we have convergence, then the series converges. If we have divergence, then the series diverges. So go back and, dust off the definition that you guys had a test on, right? And this is why you do this here. So we have t goes to infinity here. We know that the integral is going to be, this is the portion that we focus on. And you know that that integral is going to be the natural log. So if we look at the details, this is the natural log of x evaluated from 1 to t, which is the natural log of t minus the natural log of 1, where that natural log of 1 is 0. So this integral is just simply natural log t. Now, don't forget, we take the limit of that. Right? The limit as t gets big. So we're taking the limit as t gets big of the natural log of t, and you guys know that is infinity here. So we have a divergent situation here. This means that this improper integral diverges, and this is why we actually use the language, ladies and gentlemen, when you studied improper integrals, of divergence and convergence, because it's related to this integral test and related to what happens with series. So here's the integral test. If you have, remember, this is a biconditional. If you have divergence for the improper integral, well, then your series also diverges, right? Biconditional, because this statement is if and only if. Goes both directions, not one way. And what that means here is what we just showed is simply that the series they gave us, the infamous harmonic series, this is a divergent series, diverges. Okay, that is a fact now. So we can actually do something here. So I want you guys to kind of get this notation in your head as well, is that 1 over n will be infinity. And we can put n as 1, 2, and so that's something that you run across. In math and science, you run across this particular series, and you want to know that the harmonic series, a very famous harmonic series, is a divergent series. That means it doesn't add up to a finite value. Even though it's decreasing, it doesn't add up to a finite value. And that's going to be an important detail for us today. So we're going to look at this integral test in general. But this morning, I'm going to look at a few things here. There was an example way back in when we studied improper integrals. There was a question on your homework that was something like this. They gave you an example, and they said, okay, here's an improper integral. And it's 1 over x to the p dx. And the question is, for what values? And it's for what values of p do you have convergence? A very, very famous kind of question. For what values of p do you have convergence here? I want to note that we just took a look. I want you to say, here's how you really do this. You have to take cases, really. And you're going to see what I mean by cases. We already checked from p is 1, because that was the 1 over x dx. That's the power here, right? So they're trying to say, for what values of p for your power do you get convergence? Well, we certainly don't get it when p is 1, right? Because we just did that question. So here we go. That's infinity. But we have to answer for the values of p, do we get convergence? Because this is going to be very useful for us. We use the definition, remember, limit t goes to infinity, integral 1 to t, 1 over x to the p dx. So we're going to try to find the values of p that we get convergence here. And like always, we focus on this integral. And to remind you that this is x to the minus p, right? So when I integrate x to the minus p dx, I get x to the minus p plus 1 over minus p plus 1. And we're supposed to evaluate this from 1 to t. And I'm going to write this as x to the 1 minus p over 1 minus p from 1 to t. And what this gives us here is t to the 1 minus p over 1 minus p minus 1 to the 1 minus p over 1 minus p. Now remember, at this point, what we know is we can't have p be 1 here, because down here, if p is 1, we divide by 0. Now, we don't care about p being 1 because of the fact that we already checked when p is 1. Right up here, we got divergence. So when I say that we have to take cases, here's what's going to happen here. We're going to look at the case where 1 minus p is greater than 0, positive, and 1 minus p is less than 0. This is what they mean by the cases. So this is how we're going to handle this situation. It doesn't matter what p is, by the way, because this portion will be 1. So we're going to look at how to approach this. Okay. So we already looked at this case here. Now let's consider something. So let me do a little bit more algebra for this here for us. Here's what the algebra is going to look like, right? We get t 1 minus p over 1 minus p minus 1 over 1 minus p. And that's going to, we can factor out the 1 over 1 minus p, and we're left with t 1 minus p here minus 1. Okay, so let's do this here. Yeah, that's my integral. And so remember, we're about taking this limit as t goes to infinity of 1 minus p, t to the 1 minus p minus 1. And we can factor out, because we're taking the limit, it's an improper integral right up in here. And we're going to factor, or we're going to pull out our constant like I say we do. 1 minus p. Now we have that limit. T goes to infinity. T to the 1 minus p minus 1. And then by properties of limits, ladies and gentlemen, I guess we can write that down too. We get 1 over 1 minus p. Limit of the difference is difference of limits. So we have limit. T goes to infinity. T to the 1 minus p minus really the limit of 1. But you guys know a few things here, that this is 1. Okay. So what we really need to know is right in here, right? What's happening with the limit as t gets big for t to the 1 minus p. So what is this limit value? That's what we're trying to find out in gray. All right, now here's something I want you guys to remember here. Since we're taking cases, And let me really emphasize that. We're looking at this. The limit, t gets big, t to the 1 minus p. Now, focus on the power here. We're taking cases. We know if 1 minus p is greater than 0, right? 1 minus p, the power is greater than 0. We know that t to the 1 minus p will go to infinity. In other words, for this particular power here, 1 minus p, we get really divergence. Because if this whole thing goes to infinity, infinity minus 1 is still infinity, and it doesn't matter if I have that constant down there. This is a divergent situation. So what we know here is when 1 minus p, the power, is bigger than 0, we get that divergence. Well, what does that mean about p? That means 1 is less than p, or it means p is less than 1. So we know a couple of things. If p is less than 1, which is really 1 minus p being positive, we get divergence. But if I go back to the case where p is 1 here, earlier, here's what we get. We can include this. So far, I want to make sure you guys know for p being less than or equal to 1, we get divergence. So I want to look at that particular case. So here's my first case. Really the second case. The first case was when p was 1. We looked at that. This is really the second case. But for these two here, we're going to look at the opposite now. We're going to say, okay, if that 1 minus p is less than 0, it's negative. If the power we're talking about here is negative, what happens to this t to the 1 minus p? Well, very simply, that goes to 0. Because that's going to be in the denominator. So if my power here now, 1 minus p, is negative, less than 0, this goes to, this portion now doesn't go to infinity. This portion now goes to 0. And so, ladies and gentlemen, what that means is this improper integral is 1 over 1 minus p times 0 minus 1 here. You're looking up here. 0 minus that 1. And 0 minus 1 is negative 1. So the improper integral then becomes 1 over 1 minus p times negative 1, or simply 1 over p minus 1. And so what we know here is, here's a fact here. That my improper integral for 1 over x to the p dx equals 1 over p minus 1. And that's for p now. We say, what kind of p? Well, if 1 minus p is smaller than 0, what that means is p is bigger than 1. So p has to be bigger than 1 for convergence. So this is a very famous fact. P needs to be bigger than 1. And you say, okay, that fact was interesting way back in improper integrals when we studied these things. So yeah, you're going to get this p being bigger than 1. In fact, you do get that area under the curve if this was the improper integral homework. So you can let p be 2, you can let p be 3. Anything bigger than 1, we have convergence. So you might say, what does this have to do? With series, right? Well, here's what this means with series. I'm going to give you a definition here. We have a whole class of series that looks like this. 1 over n to the p, where n is 1 to infinity. And by the way, just notation-wise, sometimes you just see 1 to infinity, and that implies that there's an n there. So sometimes we write it that way. Okay, you might say, well, what does this have to do with us in series? Well, here's what this means, ladies and gentlemen. We have the definition of what we call a p-series. This is simply known as a p-series. And here's a fact. A p-series from n is 1 to infinity, 1 over n, and then it's the p power, a p-series is convergent for p being bigger than 1. Now you say, how do I know? Well, really by the integral test. You see, we integrated, right? We're using that integral test that we described up here, because the integral test would be something like this. Oh, if you see this series 1 over n to the p, they'd want you to simply integrate 1 over x to the p dx. Well, we already did. We found we get this to be 1 over p minus 1 for p being bigger than 1. We did this already. This is where we get convergence. So that means this particular series is convergent, and we actually call this a p-series. This is the definition, ladies and gentlemen. So p-series converge only for p-values bigger than 1. And that's the summary. So that's putting things together, meaning this integral test, which you use in general for to determine convergence for special types of integrals or some series. And we're going to see that. I'll give you some more examples of something like that using the integral test. But I wanted to demonstrate to you 2 very important facts. The harmonic series diverges. That's 1 over n. We showed that already. Right? This is what I wanted to show you, this important detail. Harmonic series diverges, and then give you the definition really of a p-series and the conditions in which p-series converge. It's more important than saying converge. It actually, for other p, it diverges. So we have divergence for other p. So for example, here's a big example. Here's a whole sequence of examples. You got 1 over n squared. N is 1 to infinity. We have 1 over the square root of n. We have 1 over n to the 3/2. We have 1 over n to the 0.9 power. You have 1 over n to the 1.3 power. They're going to ask you something about convergence for every one of these here, right? They're going to say, do these series converge or diverge? Well, all you got to do is recognize one important detail. These are p-series. And you might say, how do I know they're p-series? Well, because you have the definition of a p-series. It's right here. There's your definition. It's any series that looks like this, 1 over n to the p power. We just have to identify the power p. And you say, okay, well, p here, ladies and gentlemen, is the value 2. There it is. In this case, you say, I don't see a power. Well, that's actually n to the 1/2. So p here in this case is 1/2. Here they described p. P here is 3/2. Oh, P is 0.9. P is 1.3. And so you identify that you're looking at a P series. Now, you have to know the conditions for convergence of a P series. And I think we wrote that down. Oh, it's convergent here only for P being bigger than 1. So you have to know what's bigger than 1. Okay, what's larger than 1? What's larger than 1, ladies and gentlemen, is right here. And let's actually color it purple, I guess, or something. Or maybe color it blue. Larger than 1. Okay. Larger than 1. Good. Larger than 1. What that means here is that this P series converges. And it's known as a convergent P series. Convergent P series. This P series converges. It's a convergent P series. And then this P series also converges. They're simply known as convergent P series. Now, like I said, it diverges for all other values. So this particular series, and let's change that color maybe. Let's find green or something, right? Since these two values are not bigger than 1, they're in fact smaller than 1, then we know we have divergence. And that's called the divergent P series. We have a divergent P series. Diverges or divergent, however you want to call it. I will say diverges. And so, ladies and gentlemen, the integral test helps us out with these particular series here. Okay. Let me go back here really quick and put this away. Okay, let's actually look at some more examples of possibly some integral tests, but let me also remark here something here. I want to say here's something you really want to be weary about. Even if you have convergence, right? These two things are not the same. Okay, so we have AN here. They are very much not equal. So I want to warn you guys, here's a warning. And you might say, well, why do you have to warn us? Well, go back to this original question here when I drew this picture here, right? An improper integral over an interval here, we go from 1 to infinity, right? We're talking area under a curve. Area under a curve is not the same as the sum of these values here. Okay? Those are two different ideas. So even if you got convergence, it's not the same. So I'm going to warn you, sometimes people think it's the same and go, well, okay, Mr. Judge, here's the nice thing. I know the definition of a convergent P series, so why don't you tell me that I can get the sum, right? This converges, isn't the sum 1 over P minus 1? And the answer is this. Here's the point. Just because you have a convergent P series, right? 1 over n to the P, for P being, bigger than 1, the sum is not this value. I'll put that in red as well. And that's really what we're trying to say to you, is that, yeah, you can have convergence for P bigger than 1, but that doesn't mean the sum adds up to 1 over p minus 1. In other words, you know something about convergence. This is what the integral test tells us. It only tells us about convergence, but it doesn't tell us, ladies and gentlemen, what the sum is. So that's a whole other question. We don't know the sum. And in fact, if I just went back to some of these P series here, there's a lot of series where we're going to find convergence and we just don't know what the sum is. We just know it converges to a finite value. And then exploring and finding sums, that's a whole other question. You know, that's something else. You're going to have to do a whole lot of other studying to find actually the sum of these convergent series. So we're starting to get into the place where yesterday we had sums because they were geometric. We had sums using the definition of the sequence of partial sums, and we can find that limit, and we got a sum. But we're now heading into an area where we can talk about convergence and divergence. But even if we have convergence, we don't know how to get the sum. And, or in some cases, it's very difficult. You got to take other courses and learn new skills and tools to get these sums. But, that's the general warning, that don't think because you have this test that it's equal to the same value. It's not. One's area and the other was adding finite values. They're different. So you can have a convergent P series. That doesn't mean the sum is 1 over p minus 1. And we don't know the sum. And that's actually the point I really want to make. And I'm going to put that in red. Okay? We don't know these sums, but that's okay. We're just finding convergence and divergence. Now, we can estimate the sum. If, for example, we find that a series is actually convergent to a finite value, well, we can estimate that. All right, we can go out, we can estimate. So, and that's just by adding a finite number, and we get an approximation. So anyway, there's a way we can approximate this. All right, let's look at some examples of the integral tests, since we got some good work in. Give you an example. They could give you something similar. 1 over the square root n plus 4, n goes to 1 to infinity. Now, when your variable's in the denominator, ladies and gentlemen, like this case here, right, we got a variable in the denominator. I'm just going to say this portion here in the denominator means, since it's a fraction, it's going to be decreasing, so you guys know. It's decreasing. And it's strictly positive. That means every term is positive. N is 1, remember? N is 2. All these values. The terms are positive, it's decreasing, and we're going to replace that with a nice continuous function. We're going to use f of x is 1 over square root x plus 4. So you're getting the same concept. It's positive, it's decreasing here as a function. Right, so the integral test says, just integrate from 1 to infinity, 1 over the square root of x plus 4 dx, which is now that limit as t goes to infinity, 1 to t, 1 over the square root of x plus 4 dx. So this is going to your homework on improper integrals. So when we integrate this, this will be x plus 4 to the minus 1/2 dx. And of course, you're going to say, do I use u sub? Yes, you do. And u is x plus 4. And you say du is dx. Okay, by u sub, notice this integral is, we can say u to the minus 1/2 du. And then that will be u to the positive 1/2 over 1/2 to square root of u. And if we put this limit back, or this variable back, that's x plus 4. So double check here, ladies and gentlemen. And this is from 1 to t. And we end up with 2 square root t plus 4 minus 2 square root of 5. And this is that thing we have, the integral. This is, sometimes I call that I of t, because now we have to take the limit, right? Take the limit as t gets big. So the limit as t gets big of 2 square root t plus 4 minus 2 square root of 5, you guys know this is infinity. Okay. And it's infinity because as t gets big, really the square root of t plus 4 gets big. So this portion here is what we focus on, and it's a square root, and so that's going to make our limit go, wherever. That's going to make it get big, to infinity and beyond, right? Even though there's no such thing as beyond infinity. Okay. That's a pretty good example. All right. Looking at this integral test. So, I mean, let's actually say something here. This diverges, which means the series. Let's go back over here. This series here, I want to conclude here. This diverges. It's a divergent series. Okay, so there you go. And it diverges by the integral test. So let's get some integral test examples in. And they're going to give us this series here. 1 to infinity. N squared e to the minus n cubed. And really, we can say this is n squared over e to the n cubed as well. Okay. So you're going to let f of x be, because this portion here is that, or this portion, however you want to see it, that's my an, right? So we can say, oh, an is n squared e to the minus n cubed, which is your fn. So when you write down the function you have to integrate, it's simply replace the variable with x. So by the integral test, we're really just going to integrate from 1 to infinity, x squared e to the minus x cubed dx, which is the limit here as t goes to infinity, 1 to t, x squared e to the minus x cubed dx. And that's I of t. So when we integrate, again, you're going to notice we're going to use u sub, where u, ladies and gentlemen, is right here. It's minus x cubed. So u being minus x cubed gives us du dx is minus 3x squared, or we say that dx is du over minus 3x squared. So this becomes 1 to infinity x squared e to the u. We have du over minus 3x squared, and then you notice your x squareds cancel. And you end up with a minus 1/3 integral e to the u du. And we know what that is. It's minus 1/3 e to the u, which is minus 1/3 e to the, we said u was minus x cubed. We evaluate that from 1 to t. So it's minus 1/3 e to the minus t cubed plus 1/3 e to the minus 1 cubed, which we get 1/3. I'll keep the signs. Minus t cubed plus 1/3. If we plug in 1, that's really going to be minus 1. So we get 1 over e there. So this becomes 1 over 3e minus 1 over 3e to the minus t cubed. Now, this is the I of t, the integral. We have to take the limit as t gets big and see if we get convergence or divergence. So the limit as t gets big, 1 over 3 to the e, 1/3 e to the minus t cubed. Now really by properties of limits, I'm just going to go straight to the source there, or the actual way to answer our question. We have to look at this here. So here I just use properties of limits, ladies and gentlemen. The limits of a difference is difference of limits. Limit of a constant is a constant. And we're going to have to find what this limit is right here, right? So we're focusing on that limit. Now, here's what's going on. As t gets big, what do we know about minus t cubed? Where does that go? That goes to minus infinity. So what does e to the minus t cubed go to? Well, we have to look at the exponential curve. The exponential curve, if you guys remember, yeah, let's double check here. How does that exponential curve go? Let's go something like this. Anyway, let's take a look at that, right? So if this is where we're at, assuming we didn't make a mistake on this. So we say as t gets big, minus t to the cube, third power, that actually goes to minus infinity. So e to minus infinity, that looks like it's infinity. So if this here is infinity, altogether, this limit here looks like it's minus infinity. In other words, we get divergence here. So if this is divergent, we know the series is also divergent. Let me just double check. Yeah, this is looking at this here. And double checking something like this here. Anyway, okay. So let's double check our work. U sub u is minus x cubed. So minus 3x squared. Okay. So u here, minus 1/3 e to the u, minus 1/3 e to u, minus 1/3 e to the minus x cubed. Plug that t in, minus 1/3 e to the minus t cubed, plus 1/3 e to the minus 1. Okay, so 1/3 minus 1/3 e to the minus t cubed. And as t gets big, minus t cubed, that's minus infinity. So we're looking at e. Oh, there it is. Thank you. Thank you, Marbella. Thank you so much. There's where the issue is. That's not right. Okay. Yeah, I'm looking. Something was bothering me about this. I'm saying, wait, what's wrong with this one? Oh, here's our exponential curve, ladies and gentlemen. There you go. That's what's bothering me. Good. Now this makes sense. All right, that was bothering me. This goes to 0. Good job, Marbella. If that goes to 0, then this limit, this is convergent. Let's see what this means here. What this really means is this limit's going to equal 1 over 3 to the e. And that's a finite value, so we have convergence. So yes, thank you, Marbella. I was looking that over and going, something's bothering me about this question here. This converges here. Oh, wrong one. We go back to the series. That means our series converges. There we go. So this is using the integral test. Yep, we're going to use the exponential curve. Thank you. Okay, great. There it is. All right, so that's the example of our integral test. So we can see a lot of different kinds of situations by this integral test. Let's look at some more here. Something that's kind of interesting. Okay. Here's an example. They're going to try to give you, I can see something like 1 plus 1 over maybe 2 square root of 2 plus 1 over 3 square root of 3, and so on. So they're giving you here an infinite sum, and they're going to ask whether this converges or diverges. So I'm going to say, does this converge or does it diverge? Well, for this kind of question, you have to figure out what the series is. So remember, this happens when n is 1. This happens when n is 2. This happens when n is 3. We can start to look at these terms and we can say, oh, I think this is going to be 1 over n square root of n. N is 1 to infinity. So here's our series, just by looking at the terms. And then by looking at this a little bit more, we can say, well, we're going to use some algebra here. You say, what do you mean? Well, this is really 1 over n times n to the 1/2, which is 1 over n to the 3/2. So what you end up now with is the very famous P series. And you say, oh, this is a P series. So go back to what we started the lecture with, talking about a P series. If you ever identify a P series, right, look at the power. My power here for P is 3/2. And you say, well, what do you know about 3/2? Isn't that bigger than 1? And the answer is yes. So this is a convergent P series. I don't have to integrate. So if you recognize by definition a P series and you know when a P series converges and consequently diverges, use that information. So this is a convergent situation. This is a convergent situation, and we answer the questions. All right. Let's see if we could get a few more in here. Right? So give you another example of the integral test. They give you 1/5 plus 1/8 plus 1/11 plus 1 over 14 plus 1 over 17. And then this goes on forever. Now this happens when n is 1. This is when n is 2, n is 3, n is 4, n is 5. We have to try to identify what this pattern will be, starting from n is 1 to infinity. Now I know that they differ, it starts at 5 and then it goes to 8 and then 11. So, the terms start at a point and then they differ. Well, looks differ by 3 there. Let me express to you what this is. This is 1 over 3n plus 2. Double check the terms. So you have n is 1, and that'll give you a 5. N is 2. 2 times 3 is 6 plus 2 is 8. Okay. N is 3. 9 plus 11. Yeah. All right. This is the series. And you're going to see that this is, you're going to let, if you want, you say, okay, here's my AN again. And then that means that AN is FN, or AN is 1 over 3n plus 2. You're going to use f of x, 1 over 3x plus 2. Now, this function is continuous, it's positive, and it's decreasing all over the interval from 1 to infinity. So you get to use the integral test. So let's change that color then. So we integrate 1 to infinity, 1 over 3x plus 2 dx. And by definition, that's the limit as t goes to infinity. 1 to t, 1 over 3x plus 2. I just have to integrate here. And of course, you'd have to use u sub, where u is 3x plus 2, and then du dx is 3. So I get dx going to be du over 3. So that this particular integral, called I of t, where I of t equals 1 of t, 1 over u, times 1/3 du, which is 1/3 integral 1 over u du, which is 1/3 natural log absolute value of u. And then don't forget, we're going to write this back in terms of what this is. 3x plus 2, we evaluate that from 1 to t. 1/3 natural log 3t plus 2 minus 1/3 natural log of 5. So this is I of t, and so we say as t gets big, that I of t goes to infinity, essentially because as t gets big, 3t plus 2 gets big. And then you have the natural log of that, which means natural log is an increasing function. 3t plus 2 goes to infinity. So this portion here simply gets big, right? Goes to infinity. So you end up with infinity minus this number, which equals infinity. In other words, the improper integral diverges, which means your series here diverges. This is a divergent series. All right, and then maybe to say to you, we can give you one more example of this. I got a few here. I got one more example. Or a few more. What I could do a bit later for you guys is go over maybe about, 3 or 4 more examples of this. Integral test for you guys. Or, we just go over one more and call it a day, maybe. Let's try to see if we can finish one. Anything looks interesting here? Yeah, let's try this one here. Okay, we'll try this one. 1 over all right. So again, this is not going to be a geometric series. And you might say, okay, I'm going to have to do some integral tests. Remember, this is 1 over, this is rational where the numerator is getting bigger, so the fraction is getting smaller. So this is going to be decreasing terms. So if I let here f of x be, right, 1 over x squared plus 6x plus 13, I want you guys to know this is positive, it's continuous over the interval, and it's decreasing. Now, you may have to show that's decreasing, but we know that's decreasing because of the essence of how it's defined. So I just have to integrate from 1 to infinity. 1 over x squared plus 6x plus 13 dx. Now you look at this and you say, I don't even think I can factor it, so I can't use partial fraction decomposition. So we can't even factor the denominator. Down here, right, it's not factorable. So you might say, what's something that I can do here? Guess what you can do? You can complete the square, right? 6 over 2 is 3. You're looking at that b term. And then the second step is to say 3 squared is 9. So 1 over x squared plus 6x. Don't forget to add 9 and subtract 9. That's really 0. That's not there. And then you have that plus 13. So by completing the square, ladies and gentlemen, we're going to get x plus 3 squared, because you're really supposed to factor the first 3 terms. And we did. And then you're supposed to add the last 2 terms, and that's plus 4. So you're going to integrate here from 1 to infinity dx. And yeah, over the interval, this function is continuous, it's positive, and it's decreasing. And then we can say, well, that's the limit as t gets big, 1 to t, 1 over x plus 3 squared plus 4 dx. And you guys know what's going to happen. You're going to use u sub where u is x plus 3, which means du is dx. And when you integrate, so I'm going to let you guys know what this becomes here. Here's I of t. I of t, you're going to see, well, all right, let's actually give you some detail. Yeah, that's 1 over u squared plus 4 du. Don't put the limits because the limits are in terms of x, right? So you guys know what this is. If you guys remember, this is going to be 1/2 inverse tangent u over 2, which is 1/2 inverse tangent x plus 3 over 2. Now you can put the limits. Is that right? Yeah, x plus 3 is u. So we get 1/2 inverse tangent t plus 3 over 2 minus 1/2 inverse tangent. Now 3 plus 1 is 4. That's going to be a 2. Here's your I of t. Okay, now we have to take the limit. Remember, this is an improper integral, so we take the limit here. So now we're going to say, as t gets big, we know t plus 3 over 2 gets big, and then we know that the inverse tangent here of t plus 3 over 2 goes to pi over 2. So altogether, I of t goes to 1/2 times pi over 2 minus 1/2 times the inverse tangent of 2. Or really, here's where I of t goes to. Pi over 4 minus 1/2 inverse tangent of 2. The point is this is finite. So we have convergence. It's a finite value. So by the integral test, since the improper integral converges, that means this series here also converges. Yeah, that's a good one. There's a couple of good ones. I'm not sure. I may do for you guys a little later today if I get some time. I might do an extra video that goes over about 3 or 4 problems, maybe. I don't know if I get that time. But we did get a good dose of this section into us, meaning you guys know how to integrate. You know how to do improper integrals, and so there isn't really much to go with. But I might do if there's time, I'm going to do some more for you guys. If there's not, I might do a few more. If there's not, we'll see how that goes. But I want to remark again that your homework on this section, before I give you my remark, this is 11.3. So you can do like 3, 2, 25 odd. Now, I would do them all, but that's me. And maybe you want to do you could do 3 to 25 odd. And this is on the integral test. But just to kind of remind you, go back and look. If you guys showed up a little bit late, slept a little bit in, go back and look. And definitely, I gave you guys some really good examples that they're on my website, right? If you go back here, we did series. I did a bunch of examples for you guys. I had a lot of fun doing that. And I'm going to suggest you guys definitely look over these examples here, because I do have a tremendous amount of resources there, good information about things you guys need to know from some examples, like some additional examples of telescoping series, geometric series, and the divergence test. So this is all foundational stuff that you guys are going to be tested on too. So make sure you guys watch that, okay? And if you have any questions or issues, of course, you guys know, see me in office hours, and we'll see what we can do, okay? So I hope you guys enjoyed this today. Integral test, and stay safe, work hard, go over everything you need to go over, check your grades and everything, because some of you guys are still having some trouble uploading things. And I got to tell you, at this point, you should be very knowledgeable about this stuff. So make sure you guys are functional in that way, because, in the future, we're probably not going to accept anything that's late. Anything. So make sure you guys are good to go with all those kind of things. So take care, and we'll see you tomorrow if I don't see you in office hours. All right.